And we are live. Hi, AST 111. Oh, now we're live. Hi, AST 111. My name is Frank.
My name is Bill.
And we're going to be doing roughly about an hour on our second YouTube live session. So let's see, a little bit about me, I guess. So I'm Frank. I work at ASU. I'm the instructor for the course, and professionally what I do is stars, particularly ones that go boom in the dark night sky.
And I'm Bill. I also work at ASU. I'm a postdoctoral researcher there and your TA occasionally. And I also deal with stars, specifically little stars known as white dwarfs. I'm actually coming to you live from UT Austin, where I'm at a conference for white dwarfs. I just stepped outside to do this telecon.
Got to be cooler in Austin than it is here in Phoenix at about 117 Fahrenheit today.
Yeah, I'm showing 92 right now with a high of 98. So it's it's better.
It's winter. It's winter. Oh my goodness. Okay, so general plan, what we're going to do, we're going to answer some of the questions that were posted on our discussion board. So you are free to continue to post questions, and we'll try to get to them, but we'll answer the ones that are there today. Bill, why don't you take one?
Sure. We have Renisha03 had a question. In the past, has the Earth always been rotating counterclockwise, and will it always be rotating counterclockwise even in the future? My quick answer would be yes. There's no reason to think that it's been changing. It was just sort of the angular momentum that the Earth had when it was formed. And unless you had some sort of dramatic impact to change things, I don't see why it would have. And I think it's being slowed down ever so slightly by the moon, but I don't think it's ever going to, really lose, 50% or something like that of its speed over any meaningful time scale. So it's basically always going to be going counterclockwise, but the speed may change from time to time.
Right, I agree. Yeah, it picks up the rotation sense from the solar nebula disk. So the solar nebula disk is rotating counterclockwise, and that's why you see all the planets, more or less, unless they've had a collision, rotating in the same sense as the solar nebula, so counterclockwise. So we do have some examples of things that have probably been whacked, like Venus, Uranus. So it is possible. So unless something comes in to change our angular momentum, it's going to merrily carry on. Let's see, Hamletta. So at the tender age of 50, I've done the crazy thing and just signed up for a BS honors in astronomy and planetary science with Open University in the UK. Congratulations. That's wonderful. My former education is MA in English, although I've done some high-level math in high school sometime during the Ice Age. And I've kept up with the sciences through reading and edX. Any advice you can prepare me for study? And have you worked with older students before? Yeah, and we'll leave it there. So yes, congratulations again. I think that's wonderful. And any advice? Depends what you want to do with it, where you want to go. You can take it and get your BS in astronomy and planetary sciences. That would be wonderful. I don't know if you anticipate getting a job in the field or not. Possibilities for a job at that point would be potentially something in the space industry, planetariums, things of that nature. Or if you're just taking it for because you want, that's cool too. You could consider going on and getting your PhD at the tender age of 55. And that's fine too. That would be great. Have I worked with older students? Yeah, certainly. I think I was probably one myself. Yeah, I entered undergraduate at UC Santa Barbara, so that's where I did my undergraduate. And that was after having done some other things in life. So I started my bachelor's later, and I started my PhD even later after that. And I've worked with older students before. In fact, I just had one graduate, Rick Sarmento, and Rick's probably in his, I'm going to guess, in his mid-40s, be my guess. So yeah, there are some advantages to older students. They know why they're there. They're there for a reason. They've chosen it, as opposed to just sort of, in some cases, people just float through because school is something they've always done, and so they're comfortable with it, and they just sort of move through. I
think that's been my experience with older students as well. Is they're usually there's no nonsense. There's no just trying to get through the homework just to get it done. They usually really want to get a good understanding. I think one of my favorite ones I got to grade once was some upper division astronomy course, and they came up with some answer that clearly made no physical sense. And most students would just be happy they had a number and they just hand it in. But this student said, like, no, this doesn't make sense. Okay, maybe this assumption was wrong. They do some other attempt. They get some other completely bonkers number. I think they like, no, that still doesn't make sense. Let me try another one. And then I think I just ended up giving them full credit because I'm like, you know what? No one ever even checks to see if these answers are right. And I think that's pretty common among the older students that I've been working with.
Yeah, at least they've realized the number doesn't make any physical sense, and so at least they've got that awareness. And okay, let's try something that might make more sense. So so good luck with your studies. Hope it all goes well. Hope you do smashingly well.
And I think if you have difficulty early on, just because it's maybe been a long time since you've seen some of the concepts or since you've dealt with some of the math, I think once you get over that initial hump, then you'll be the same as everyone else in terms of your background. And if someone just came out of taking some calculus courses and you haven't seen any of this math in a long time, I think at the beginning it will be hard, but once you get through a semester or so, I would imagine you'd be more or less caught up. So I would urge you to be persistent, at least in the early years.
Yeah. I suppose my general advice would be, since you will have some electives, I would take some extra electives in math. In part because that makes the astronomy and astrophysics easier. You don't have to worry so much about executing the mechanics. You'll already have that, and so you can a little bit more concentrate on the physical aspects of what you're doing, as opposed to, oh goodness, how do I integrate this function? So yeah, cool. Bill, why don't you take another one?
Tommy Tybalt, in a series of questions, asks, is there another astronomy course after this one that's available to be taken online? I purchased the textbook and see a whole big section on black holes, galaxies, quasars, and celestial objects, and was wondering if you were lecturing a course on that as well. I've got to say that I really love taking this course. Well, thank you, Tommy. The short answer is no. The long answer is there is a second course after this in ASU's catalog, AST 112, that deals with a lot of those topics, but it is not available through edX. However, there are a bunch of other courses. I was just looking through, just searching on astronomy, and ANU, I think Australian National University, they have a whole series of astronomy courses. They have a cosmology course, the Violent Universe, and there's a number of other different astronomy courses. So if you wanted to look around, you could find some other ones, but in terms of continuity with this class directly, no, that is not offered on edX right now.
Right, and the other thing that sets this course off in edX that is unique is that this course is for college credit, eligible. Right, you can elect to take it. So it's as you have noticed, it's a real college course. There's weekly homeworks, there's labs, there's graded stuff, there's exams. So it's the real deal, and that really sets it apart from other stuff on edX where it's sort of at your own pace, or it's not graded, or it's there for edification as opposed to college credit. Let's see, Tommy also asked, I was wondering if there was such a planet called Planet X, which would be beyond Pluto. I've heard lots of different things about it being real, and I was wondering if it could be a planet in our solar system. Would have to be a Jovian. And would orbital resonance have something to do with this? Okay, Planet X. Planet X is currently hypothetical. It is expected to be sort of an Earth mass, Neptune mass. type planet that is orbiting roughly out in the inner parts of the Oort cloud, so beyond Pluto. There are good reasons to believe it might be real, or at least there are compelling, let me rephrase that. There are compelling reasons to look for it. It's not just somebody dreamt something up, like Mike Brown at Caltech, dreamed something up and everybody's all of a sudden going to go spend all kinds of time and money and telescopes and people looking for this thing. So there are reasons, particularly having to do with the tilt of the solar system, why people are looking for it. It has not been found yet, but it is an active area of research. The evidence keeps mounting that something is there, although you're starting to see some pushback in the literature that, well, maybe it's not. So it's a tale TBD, to be determined. But I will say that the sensitivity of our instruments, our ability to detect really low luminosity events, has improved dramatically over the past decade. And so it's definitely within our technical capability of finding them. And in fact, one of the things that we just posted in the discussion board was the discovery of 12 new moons of Jupiter. And those were discovered while looking for things like Planet X. So they just happened to be bonus discoveries that came in while you were looking for what you were really looking for. So that's great. Yeah, orbital resonances probably had something to do with this, of pushing the purported Planet X out of its original orbit out into the inner parts of the Oort cloud. So yes, it had a gravitational scattering event that pushed it out. There's some terminology for you there.
There's a pretty good Wikipedia page on this. Actually, I was just reading it, preparing for today, and it.
Oh, okay.
I think they call it. I think the page I was looking at was Planet 9, and then there is some hubbub of, oh, well, that's just negating the effects of finding Pluto, and it's disrespectful. So then someone said, call it Planet X, and so you can find sort of terminology on both. But there's a good roundup of all the evidence and all the sort of problems that this planet would solve. But then they're very, very clear, which I appreciated, that this planet doesn't exist until it's detected directly. Hence why it doesn't have a real name yet.
Correct.
All right.
So yeah, I will be bold and make a bet that we will probably have a definitive answer within the decade.
Could you have a definitive no? Is that possible?
No.
You're saying it will exist within a decade.
But okay, let me rephrase that. I would say a significant part of the available search space will be searched, will have been searched. So you can never say no, but you can really constrain its existence, let's put it that way.
Yeah, I'm sure there's lots of people hunting for this thing.
All right.
Tommy's got some more comments for us. I'll just do the first one here, but a question a little bit off topic, but still dealing with astronomy. I know that our sun is too small to turn into a black hole, but could a black hole from another place move? And if so, could there be any coming towards our solar system? In short, yes, that is physically possible. So black holes are formed when a star explodes. Frank could tell you all about that. But usually that explosion is not totally spherically symmetrical. So there's some, we call it a kick velocity. And so these things are kind of moving in orbits that don't necessarily make sense in terms of the galaxy. They're not just smoothly going around. They might be zooming across, and I don't know, can they even be unbound from the galaxy and just fly off into intergalactic space? I don't know if you get enough energy to do that.
I don't think you get enough energy to do that.
But still, to go on very strange orbits. So yeah, something could just get launched, straight at us, but there's no evidence. Although I guess if it were just a lone black hole, we wouldn't really see it, would we?
Nope.
So in theory possible, but that's throwing a dart at a dartboard, much bigger than the ocean, and trying to hit a bullseye.
Hey, I think we had a homework question like that this last week. Exactly.
Yeah. So yes, unlikely, but actually possible. There could just be rogue black holes flying around that you can't see.
Yeah, within the last year, we just had a visitor from another solar system. I'm sure I'm butchering the pronunciation. Oumuamua. Sure, I said that wrong. Yeah, we had a visitor from another solar system. So yeah, these things are possible. Oh yeah, and there's a second one. So why are galaxies moving apart so quickly? I know Andromeda M31 should be colliding with the Milky Way in approximately 2 billion years, and makes me wonder about these galaxies. Yes, galaxies are moving apart from one another. I don't know about so quickly. You'd have to say relative to what. But all the galaxies are moving apart from one another. This is the expansion of the universe. So that's in general. In large scale, galaxies are moving away from one another. However, locally, you can have different events, and so galaxies do tend to merge. They have gravity, and so gravity does its thing and causes things to merge, and that is happening with Andromeda and the Milky Way. So are the two big spiral galaxies in the local group, our local group of galaxies. And so yeah, in roughly 2, maybe more like 5, depending how you want to define it, billion years, the Andromeda and the Milky Way will undergo a merger event. That's also about the time scale when the sun will begin to die. So it'll start to bloat, turn into a big red star. So it'll be an interesting place on Earth in about 5 billion years. Galaxies colliding, stars dying.
Oceans boiling.
Oceans boiling. Presumably humans, or some rendition of humans, living out our science fiction fantasies, trucking around, so we won't be too worried about that. So interesting, as Bill mentioned, you know, the cross sections to these things for collision is incredibly small because space is so very big. So the canonical, to 0th order and probably even first order, galaxies collide, but stars in those galaxies do not collide. Will you find the occasional rare case? Absolutely. But in general, they're like two ghost ships passing one another. They will, of course, not be spiral galaxies at the end. They will be perturbed, probably ending up in sort of a spheroidal shape at the end of the merger. But yeah, fun stuff. Okay, I think that's got us through questions that are posted so far. I'll do a quick refresh. And no more new questions. So we're at 10:18, and Bill and I have some sent. We'll just sort of go through it and see where we're at in time. So
okay.
Bill, why don't you go?
See if I can successfully screen share. Looks like I can. So is this working?
I do see. Well, I did see your slides. Maybe I
think I need to make it a full screen share rather than just one application.
Okay, and I'm going to mute once you get it up.
Entire screen. Okay, that looks right. Let me play this. Okay, Frank, you can let me know if it doesn't show the whole thing, but I'm assuming it's fine.
Looks good, and I'm muting.
Okay, so this is a bit of a fun topic, a little bit away from the precise science that you're all going through, but it's always one that sort of animates people's imaginations. The idea of how, in the event that we wanted to contact extraterrestrial intelligence or receive contact from them, how would we do that? And actually, whenever I hear the word contact, I immediately think of the actual book by Carl Sagan that was turned into a movie, which you may or may not like. I enjoyed the movie. Some people didn't like how it ended. But in this case, aliens made contact with Earth. I believe they detected it through the Very Large Array in New Mexico. And by sending a sequence of sort of, in this case, it was showed as sound signals. You don't actually listen to radio telescopes, but whatever, it made for a good movie scene. And they basically sent a sequence of pulses that was increasing prime numbers. And so that sort of, indicated this isn't some weird natural process. This is some form of intelligence sending some information. And then there was a bunch of information encoded deeply and strangely in these radio pulses that were sent. And so I like that idea of this sort of clever way of encoding things using math or whatever to that should be a universal language. So That's sort of the idea. And actually, as it turns out, we have sent some messages, usually more celebrations rather than a real attempt at making contact with extraterrestrial intelligence. But usually math becomes sort of the basis. You need to start from some basics of math and some basic physical fundamental constants, like some wavelength of a particular transition in an atom or something to that effect. And then we can use that to build up kind of a language to speak. And so first I'll talk about this telescope. It used to be the biggest radio telescope in the world. Maybe you've seen it in various movies. I believe it shows up in a dramatic fight scene in Goldeneye, classic Bond film. But for a very long time, since it was built in 1961, it was the largest telescope of any kind in the world, although it was just recently outdone in size by an even larger radio telescope in China in 2016. But in 1974, 13 years into its life, some significant upgrades were made to expand the different frequencies it could receive and send. And so they commissioned a celebration to beam a message, the Arecibo message. A version of that is what's seen on the right. It was constructed primarily by Frank Drake. You may have heard of the Drake equation, which is sort of this way of estimating how many different extraterrestrial civilizations that we could communicate with that would be accessible to us. Some very rough estimations, but he sort of really spent some time thinking about this. And then Carl Sagan, who you may have heard of, and then some others helped develop this message. And so they sort of had to start really basically and figure out how they could send something that would be understandable. It was beamed via Arecibo towards M13, which is a cluster of stars. It's relatively close. It's not really close enough to matter, as I'll talk about later, but it was considered that would be the place where this message could actually get through. And this picture on the right looks all nice and colored, but actually what you can send, you can't just send a picture. All you can send is, in this case, they sent ones and zeros, basically sending a message where the frequency would go up and down, up and down. If it was up, it was a 1. If it's down, it's a 0. And then it changed, some number of times per second. And I think it took about 3 minutes to send the entire message. So these colors in the picture on the right are entirely artificial. You should probably just think of it as being white and black, but they'll be helpful as I explain what the message actually is meant to convey. So yeah, like I said, the listener just is going to see zeros and ones as they receive this, and then somehow they've got to be able to figure out, from just this giant sequence of zeros and ones, how to get something useful out of it. And a hint that probably doesn't seem like much of a hint is that the length of numbers, lengths of zeros and ones, is 1,679. And that number actually has a useful property. It is semi-prime, which means it's the product of two prime numbers, and there's no other way to factor it down. So then you can arrange this into a rectangle that's 23 wide by 73 tall. That's the image on the right. You could also do it in the other order, where it's 73 wide and 23 tall. That's the picture on the bottom. And that kind of looks like gibberish, whereas the thing on the right clearly has some structure and some space and some pictures and things like that. So the idea that some other civilization would probably be able to figure out which of these two it should be. And then I'll go through what these things actually mean. So the very top level, all these white boxes, are actually the numbers 1 through 10 in binary. So each white dot along the bottom is indicating that there's a new number. And then we actually get to use our base 2, here are the numbers, to figure out what it is. So basically it becomes an addition problem, where the very first row above the dot is your 2 to the 0 spot, so 1. And then above that is your 2 to the 1, 2, and 2 to the 4. And then you add them together. So you can see how 1 just has that first dot filled, and then 2 just has the second one filled. 3 has the first and second, so it has 1 and 2, so 3. And so on, we go on. And then eventually when we get to 7, we have to use all 3 dots, so then we have to move into a new row. And so that ends up being 2 to the 3rd, and then we actually don't need to go higher than that to get to 10. But this sort of establishes a language of numbers and how we can, now we can at least communicate numbers by using these ones and zeros. Okay, so then they wanted to tell a little bit about us. And so this is actually a sequence of numbers. It's 1, 6, 7, 8, and 15. And the reason that they chose those numbers is because they're the atomic numbers of hydrogen, carbon, nitrogen, oxygen, and phosphorus, which are the main ingredients in DNA. So we're trying to communicate something about humanity here. And so now we've sort of established this as a new code where these different columns are the different elements: hydrogen, carbon, nitrogen, oxygen, and phosphorus. So now with that, I have to make a little bit of a leap where now each of these little green things are recipes for different nucleotides and sugars, so the sugars and bases in the nucleotides of DNA. And so this first one, now the columns, instead of being numbers, are the atomic components of DNA. So H, C, N, O, and P. The very first one, we have the 1, 2, and 4 spots filled. So there's 7 hydrogen. Then for carbon, we have 5, and then no nitrogen, no phosphorus, and 1 oxygen. And that's actually deoxyribose. And then there's a bunch of other things, but sort of trying to communicate, this is the thing that makes us, are these chemical compounds that can be made. And presumably these elements should be available pretty universally. Okay, so then now on this picture, we have all the different bases and sugars on the top, and then the middle is a little bit more of a picture, actually. So the blue is showing the sort of double helix structure, and the middle column of whites actually is still just one giant binary number, about 4.3 billion, which was thought, and I believe still is, I guess I don't really know my biology well enough, about 4.3 billion, the number of nucleotides in the human genome. So again, just communicating a little bit more about what we are on the cellular level. Then probably the most obvious feature is this typical human here. That really is just a picture. There's nothing encoded there. But on the left, that was the number 14, and that actually is expressed in the units of the wavelength that this message was sent. 14 times that wavelength was about 1.75 meters, the typical height of a human. That'd be a little bit of a stretch for me to figure out what that means, but there it is. And then on the right is, again, one giant binary number giving roughly the human population at the time that it was sent, something on the order of a few billion. Could go through and figure that out if you really wanted to. All right, and then there was another sort of pictorial thing showing the solar system, where the number of blocks for each planet or the sun is some rough estimate of how big they are. It's not really to scale, but you can see the third one, the third rock from the sun, if you will, is elevated to sort of indicate this is home. And then the very bottom of the message was a depiction of the Arecibo telescope that sent the message. The bottom middle actually gives the diameter read horizontally, so I believe the dot on the lower right, I think, is indicating the start, 2,430, which is, again, in units of the message wavelength, the width of the Arecibo telescope, 306 meters, roughly. And that's the end of the message. So it was sent to M13, which is 25,000 light years away. So we're, 40 years deep here. So it just has another more or less 25,000 years to go before it gets there. And any return message, if it did come back, would take yet another 25,000. So not really a full-throated attempt to contact these alien civilizations, but I think it was more of a celebration of the capabilities of Arecibo and kind of a celebration of humanity in general. And I personally just find it a very clever use of trying to figure out how can I work with so little to try and communicate something. And I imagine if something like this arrived here, given enough time, we could probably decode this message and figure out what someone was trying to tell us. I'll talk about one other attempt to communicate. Again, more of a celebration, but there's the Golden Record. Actually, 2 of these went out on the Voyager spacecrafts in the 70s. And actually before that, the Pioneer spacecraft went out. I think they just had some plaques on them that had some information, but they actually made a record that you could play and get data off of. I like this line from Carl Sagan, who was, again, I think he was the sort of lead designer for this, but had a lot of help from others. Said, "The spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet." I think that's kind of a nice gesture. And it was also during a time when everyone was worried about the USSR and the United States blowing each other up. So it's kind of a nice, happy moment in our history. So here's what part of the record looks like. There was images encoded on it. Again, they were encoded in a similar way where they give these lines and columns of ones and zeros that give a picture. And then eventually there's actual sounds that you could play. There's laughter, there's greetings in a bunch of languages. There's a lot of natural sounds. They tried to get a wide amount of diversity in the music they chose, and then the languages and locations that they recorded all these things from. And there was actually an entire hour of Anne Druyan's brainwaves. She was Carl Sagan's wife. And then etched onto the record here, on the right, there's all these different images that are more or less instructions on how actually to play the record. So in the upper left, it's telling you something about the, there's some binary code in there, and then it's talking about the hydrogen atom and using that as a way to tell you how fast to spin the record. In the upper right, and I think middle right, is showing you how to actually read off the zeros and ones in the initial pictures, how long the typical bit should be, how long, what amount of time it takes, and then how to turn it into a picture, and then indicating that the very first picture you should see is a circle. That's sort of the middle on the right there. And then actually in the lower left, it's a map of pulsars. Each of these little lines are indicating a distance to a pulsar, and then the line itself indicates how fast the pulsar. There are these weird pulsing neutron stars that are almost perfect clocks, and so if you were able to say, like, okay, the 35 millisecond pulsar, people in the local universe should be able to find which one you're talking about. There's not going to be that many, and then this creates an accurate map to find Earth. So Voyager 1 actually will pass within 1.6 light years of a star, so, not really all that close. If they were like us, we don't notice random junk flying at 1.6 light years away, and that's about as good as it's going to get, and that's not going to be for another 40,000 years. And it's really not going to go near anything, and Voyager 2, really nothing in its future. So again, this is more just a celebration of Earth and humanity, and not really practically reaching out to other civilizations in the universe. But I still find these ideas really clever and a good kind of engineering problem to figure out how you would communicate things and how you would talk to aliens and figure out a language that you could both speak. I think that might be all. Yep, that's all I've got for now. So I'll yield back the screen.
So you mentioned that the Arecibo message was sent to M13, and I think that's a cluster of stars.
Yes.
Called the globular cluster, if I remember right.
Yeah, it's a globular.
What was the motivation for sending it there as opposed to somewhere else?
I think it was a nearby globular cluster that had a lot of stars. So the idea being like, this should get to a large number of places that might host planets. Although I think in the center of a globular cluster, there's probably a lot of gravitational interactions that would probably rip the planets away. But yeah, I'm not entirely certain. That would be my guess, just because there's the largest number of stars in a relatively close place.
Got it. That makes sense. I remember reading science fiction somewhere, an imaginary planet in a globular cluster. Not too close, but not at the outskirts either. And there's so many stars that there was almost no nighttime.
I think Carl Sagan also had the line, and it was like, imagine living in a globular cluster, and instead of having a sunrise, you'd have a galaxy rise because you're outside of the Milky Way, and you have this beautiful view from the top down, and it's quite romantic as well.
Cool. Okay. Let's see, I don't see any new questions, so I'm going to cover one myself, something that didn't make it into the edX version of my take on AST111X. So let's see, screen share. I guess I'll just share the whole desktop. Start screen share. Play. Oops. That's not what I wanted. How's that look?
Yeah, it looks good. All right, I'll mute.
I will go. So yeah, this is a module on the sun, which is a topic that for various reasons got dropped in the Global Freshman Academy version, so we'll cover a little bit about the sun. So all cannot live on the piazza, but everyone may enjoy the sun. There's a Italian piazza, very colorful, purples, yellows, oranges. So what I want to do today is we're going to take a journey from Earth to the center of the sun and back. So we're going to get on our spaceship, and Carl Sagan had an imaginary spaceship too in some of those Cosmos series. And we're going to blast off to the center of the sun. So as we sort of start our journey to the sun appears to be a ball of glowing gas. And the total power output from that sun, which we call its luminosity, but a luminosity is power, same thing, is an amazing about 10 to the 26 watts. That's 10 to the 26 joules per second. That's a whole lot of energy coming out of a garden variety star like the sun. And if we could capture and store just 1 second of the sun's total luminosity, it would meet our current energy needs for about the next 500,000 years or so. So there's a big energy source in the sky that we're not really tapping all that well yet. Yeah. So of course, as you've done several homework problems now, lab problems on this, the Earth only intercepts a tiny fraction of the sun's total energy output because the Earth only covers a very tiny part of a disk relative to the size of the sphere at Earth's distance. And the rest, in some sense, goes wasted as far as humanity is concerned. And it disperses in all directions from space. And so the image here is the sun in both what is called H alpha. So you put a filter on that eliminates all light except light from a very narrow wavelength around where hydrogen has a transition. And the sun is also shown in white here. And of course, you see those dark spots on there. Those are the sunspots, and we'll talk about sunspots in a little bit. You can also see some flaring on the left there, those red flares coming off and prominences coming off the surface of the sun. And we'll get to those in a little bit too. So most of the energy that we receive on Earth is in the form of visible light. But once we leave the protective blanket of Earth's atmosphere, as we go toward the center of the sun, we're going to encounter other types of radiation, including ultraviolet and X-rays. And here's an example of what the sun looks like in high energy X-rays. This is from NASA's New Star satellite, and it's color coded by the type of energy coming out. And so in this particular rendition, blue is higher energy, redder is lower energy. And so you can see you've got these sort of high energy vents coming out from what look like holes. Those are some of the sunspots. Looking at the sun obliquely there. Okay. So as we head, we're going to need some shielding from our spacecraft to prevent some serious burns from all these high energy forms of light. And I just kind of like this image. It sort of shows our past spaceships, our current spaceships sitting there, and sort of where our science fiction points us to there on at least interstellar travel as we go between. So as we head out toward the sun outside the Earth's atmosphere, we can look through a telescope at the sun, and using spectroscopy, which you know what that is, you can see that the sun's surface is made mostly of hydrogen, about 70%, roughly about 30% of helium, and 2% of everything else. So that's the carbon, the oxygen, the silicon, the iron, all the good stuff that helps make you and me. So that's the 2% of the heavier elements that were in the solar nebula when the sun was formed. And you should recognize this pattern here. This is a continuous spectrum, the rainbow from red to purple, with various dark lines, each of those representing a transition as a photon from the interior of the sun is absorbed in the atmosphere, punching a hole in the continuous spectrum. And it's from this fingerprint that we determine the elements that are in the sun. And in fact, this is how helium was discovered. And helium is a relatively rare commodity on Earth because it's relatively light and it escapes fairly easily. And so the element helium number 2 in the periodic table, was discovered by looking at the sun. Helium, Helios, the sun, that's where it gets its name. Okay. Also looking at a telescope, we can see that the sun is seething with churning gases, and there's at least a few sunspots that are blotching the surface, and they also move across the surface of the sun. So you have a sequence of images here over about a 5-day period, and you can see those sunspots boogieing across from left to right on the sun in a group. And just for reference, in the bottom picture, there's sort of the size of the Earth. So these things are much bigger than the size of the Earth as they move across. And although the sunspots look dark in these pictures, they only look dark because they're relatively cooler than the surrounding gases. If you were just to look at a sunspot, they would be blindingly bright. It's just in relative to what's around them, they look cooler. They are cooler and hence look darker than the surrounding material. So the sunspots are one way that we get a handle on how fast the sun is rotating. And so what you find, it's not the only way, but it's one way. And so what you find is that at the equator of the sun, that takes about 25 days to go around. And the time it takes to go around, how fast the sun is rotating, increases up until you get around on the North and South Pole, where it takes about 10 days longer, about 35 days to rotate around. So this is kind of like watching clouds on Jupiter or Saturn to determine a rotation rate, except rather than clouds, here you're using sunspots, so markers on the surface, basically, of the object to measure a rotation rate. So the sun is not a solid ball. If it was a solid ball, everything would spin at the same rate. And so the sun is doing what we call differential rotation, meaning that different latitudes have different rotation rates. And that tells us something a little bit about not only the surface of the sun, but perhaps about the interior of the sun. So as we continue toward the sun, the headwinds get ever stronger as we get there, and those headwinds are called the solar wind. They form sort of a drag on our spaceship as we make our way to the core. And this solar wind is created by photons that exert some pressure, but mainly particles, right? So things like protons, helium nuclei, electrons, these things, all these particles are being pushed out from the surface of the sun, just as they have been ever since the sun was formed from the solar nebula. In the past, the solar wind was a lot more powerful as it cleared out the solar nebula. And so these days it's a bit smaller, or weaker, I should say, as the sun ages. So this is a great little diagram of the sun, the cutaway of the sun and the various components of the sun. We're going to hit this diagram a couple of times. So we're out at the solar wind. We're going to head into the corona, then the chromosphere, then the photosphere, the convective zone, the radiative zone, and finally the core. And we'll take a look at a few of the surface features as we already have on sunspots and flares and prominences and all that good stuff. So this diagram actually comes from Wikipedia. It's a nice little diagram if you want to pick it up and study it in a little bit more detail. So that solar wind is very important, particularly if a planet does or does not have an internal magnetic field. In the case of Mars, shown on the left here, Mars is geologically inactive as far as generating a magnetic field, so that solar wind comes impinging on in unabated and is responsible for stripping away most of Mars's atmosphere. There's no protective sheath. On the other hand, Earth has a moving fluid on the inside. It's still warm, and so you got something electrically conducting and rotating, and that means a magnetic field, and we have a fairly robust magnetic field that acts like a giant shield from all those particles coming in and hitting the surface of the Earth. So that's a nice little protective sheath that we get from the solar wind. So roughly about 1 million kilometers above the solar surface, we enter the first, quote, layer of the sun, which is called the corona. This is a very tenuous uppermost layer of the sun's atmosphere. And you can really get a nice shot of the corona during a total solar eclipse, as is shown here. This is a real image. It's not just the moon plunked on top of the sun. So if you ever get a chance to see totality, do it. It's a pretty cool experience. And you can really see the corona, and you can see the prominences. You can see the red flares coming off. It's a sight to see. So there's the corona. It's the most outer layer. The temperature in the corona is about 1 million degrees. It's really hot. It's almost as hot as the center of the sun in those outer layers. However, in our spacecraft, we don't feel that heat too much because the density is so low. So particles have a whole lot of energy. They're moving around quite quickly, but their density is low. So high heat, low density, not much heat transferred. But it's the corona is where most of the sun's X-rays are emitted. And the image here is an X-ray image of the sun with the different colors corresponding to different temperatures. So red here is the highest energy X-rays, and blue is the lowest energy X-rays. And you can see it's not uniform. It kind of looks like a pizza, a red-blue pizza as it goes through. Okay, and so that's how we study the sun in X-rays, is looking at the corona. So farther in, as you move in from the corona, the temperature suddenly drops to about 10,000 degrees in the chromosphere. And the chromosphere, that stands for the color sphere, that's chromo, color. And this is where the sun is going to emit most of its ultraviolet. And moving further in, we're going to come to the photosphere, which is what we see. This is the sphere of visible light, photovisible sphere. And so you can tell that as you go in to the sun, you go from a high energy emission, X-rays, to lower energy emission, UV, to visible light as you head on in. Okay. And so as I mentioned, the chromosphere is a primary source of the sun's ultraviolet, and this is just a wonderful art science picture on the structure of magnetic filaments in the ultraviolet in the chromosphere. You can see spicules. There's a lot of pattern there generated from the magnetic field, which we'll get to in a bit. Speaking of, we'll get to it right now. So as we go into the sun, our compass is going absolutely nuts as we descend through the solar atmosphere, and particularly the chromosphere, indicating that the solar weather is shaped by intense magnetic fields. This is a somewhat state-of-the-art calculation of the magnetic field structures in the solar atmosphere, with red here being the most intense magnetic field and blues being a weaker magnetic field. And so you can sort of get these structures. Okay, it's not uniform, it's not constant. They tend to group into various fields from the turbulence, the convection that's taking place. Okay. So occasionally, huge magnetic storms occur, and they shoot these hot gases out into space, and we call these things flares. We call them prominences, and there's other activities as well. And so this is a shot of the sun in the ultraviolet, and you can see on to the right, there's these looping structures. Those are the prominences. You can actually see those with your eye during totality. Don't look at the sun if it's not totality, but you can see the red, what look like red looping flares to your eye from there. You can also notice the sunspots in this picture. This is sort of acting as the source points for where magnetic field is coming out of the sunspots. And this fact, this is probably what drives them to be cooler and darker. So there's an intimate relationship between sunspots and magnetic field that emanates out of and into the sunspots. And at last, as our journey goes in, we reach the visible light surface of the sun. This is called the photosphere. Temperature of the photosphere is about 6,000 Kelvin, so a good deal cooler than the corona or the chromosphere. lovely image of a jet and its contrails going across the sun with sunspots. And so when we say the sun, this is what we see. We see the photosphere. This is where the visible light comes from. And as we dip below the photosphere, we find that our spaceship is tossed around by this incredible amounts of turbulence. We see hot gases rising up, cooler gases cascading downwards, and we are in the convection zone. Okay, and this is where energy from the sun is transported by moving material. So we move material up, we move material, cool it off, move it back down where it heats up, and you complete that conveyor belt. And that is how energy is transported in the convective zone. It's turbulent, it's boiling, it's roiling. And so this photosphere is now above us, as we're now formally inside the sun. And you can see that the photosphere is sort of the top layer of the convective zone. So it's like the top of the boiling pot. And this is why when you look at the sun, you see sort of this granulation pattern shown here in this image from the vacuum tower telescope that looks like, you know, something's boiling, right? You can see white areas where hot gases are coming up, and then there's darker areas surrounding those white areas. This is the cooler gases that are falling back down. So you get this boiling, roiling appearance. And of course, there's a lovely sunspot right smack in the middle of this image, showing some of the magnetic structure, and that in the center of that spot, it's even cooler, darker, where most of the magnetic field is coming out. So this photosphere, besides being the surface of visible light, is sort of the top of the convective zone, giving that roiling, boiling appearance. So about a third of the way through to the center, this roiling, turbulent region gives way to a much smoother, calmer radiation zone. And here, energy is transported outward by diffusion, which is a very smooth process. It's the diffusion of photons. As those photons make their way out from the center of the sun out to the surface. So this is another image showing the cutaway of the various regions of the sun. So we've gone through the corona, we've gone through the chromosphere, we've gone through the photosphere, the convection zone. Now we're in the radiative zone where photons move, bounce around on their way out. And finally, we plunge down to the core. So at the center of the sun, the temperature is about 15 million Kelvin. The density is about 100 times that of water. And we are at the heart of the energy producing region of the sun. And this is another cutaway of the sun, this time in hemispheres, showing the various components, convective zone, radiative zone, the core of the sun. And one way that we learn about the core and the interior structure of the sun, so you may ask, how do we know this stuff? Well, we know this stuff. One way we know this stuff is by looking at sunquakes. Okay? Much like earthquakes on Earth, we know about the structure of the Earth from earthquakes because we can detect those sound waves rattling around, and how they rattle around tells us about the density structure of the interior of the Earth. And you can do the same thing with the sun. Those sound waves bounce around not all the time. The most prominent one in the sun causes the sun to vibrate on 5-minute time scales. So if the sun is sort of a big ball of jelly or gases, it sort of oscillates on sort of 5-minute time scales, being one of the more dominant components of the sound waves bouncing around inside the sun. So unlike the Earth, on the Earth we can put seismometers, so we can't quite do that. But what we can do is we can detect those vibrations, those expanding as the sun expands a little bit and contracts a little bit. This ball of jelly is shaking around, so we can detect that shaking around by measuring the light from the sun. As it goes out a little bit, it will dim a little bit, and as it goes back in, it gets a little bit brighter, and so you can catch these little brightness fluctuations. And these little brightness fluctuations are in fact from sound waves bouncing inside the sun, and so that's how we get it. And so we call it seismology on Earth. When we apply the same techniques to the sun, we call it helioseismology, and it is from here that we can construct what is going on in the sun through the convective zone and the radiative zone. Can't get to the core with this method, not directly, but it gives us a good fraction of the radius of the sun as we go through. So you see this characteristic pattern on the left. So this is the pattern that you get from sending out waves, resonant waves. It's like a resonant cavity inside the sun, and so you get this particular pattern. Red is moving out, blue is moving in on this particular diagram. And for those who like the time domain, I put in a little animation to the left as these waves move around in the sun. Again, red being, well, it's flipped here. Red is moving in, blue is moving out, so different color scale here. And of course, it's greatly distorted in this animation, right? The sun is pretty spherical, so it's not quite as lumpy bumpy as that animation indicates, but it's meant there to enunciate the process. So another way to study the sun, and in particular study the core of the sun, is to observe particles that are called neutrinos. And these are things that come out from the fusion reactions that power the sun. So the sun is primarily powered by proton plus proton coming together. Ultimately, you take two of those and you make a helium nucleus. And as part of that process, that nuclear process, you get these particles that are called neutrinos. And these neutrinos hardly interact with anything. In fact, by the time I speak this sentence, about 10 to the 18th solar neutrinos are going to go pulsing through your body. But fortunately, because neutrinos do not interact much, you're not going to suffer any damage to your DNA or your skin or otherwise. Which isn't to say neutrinos do not interact at all. Sometimes they do. It's very small, but they do. And you can capture those small ones. So here's an example of, if it looks kind of spaceshipy, that's kind of about right. This is the Borexino detector. This is buried deep in the mountains of Italy. Your detector is on the inside, and all of these like lamp-looking things, they are looking for types of light that will flash when a neutrino comes in and interacts with the material that's inside that hemisphere region. And it's from these solar neutrinos that you can construct what is going on in the core. This is another neutrino detector. This is a large tank that's in Japan. And each of those tubes there is a photomultiplier tube, and we learned about photomultiplier tubes when we talked about detectors and telescopes. And so they are also looking for when a neutrino occasionally interacts with the ultra pure water that is in this tank. It will send out a particular type of light, and these photomultiplier tubes will pick up those effectively sonic booms from material light traveling faster than it should in water. So it's the equivalent of a light sonic boom, and that's what they pick up. And that tells us about what the conditions of the sun are. That's how we know it's 15 million degrees, density about 100 times that of water. So inside the core, we've now got a nuclear reaction going on, and besides neutrinos, we also make a high energy gamma ray photon. And that high energy gamma ray photon only travels about a millimeter or so before it collides with something, usually an electron. And so they bounce around. So each collision with an electron, mainly, sends the photon off in a different random direction in a haphazard way. It also loses a little bit of energy during that collision with an electron. So the electron gains some energy, the photon loses a little bit of energy. And so it sort of does this random walk as it's produced in the core all the way out to the surface of the sun. And so that one gamma ray photon created in the core takes on the order of about 1 million years to make its way to the surface of the sun in this random drunken walk as it goes through. And what was originally a high energy gamma ray now gives way, is transformed into about 1,600 photons of visible light as it comes on out. That visible light leaves the surface of the sun, and we complete our journey from Earth to the center of the sun and back, as those photons come back as a essential energy source for weather and life on the blue marble. That's what I had to say about the sun. So let's see, screen sharing.
Perfect timing.
Oh yeah, we're good. Super. Let's do one final check, see if we got any questions. Otherwise, no, we're good. All right, awesome. Bill, thank you very much for doing today's YouTube live session.
Absolutely.
And thank you everyone for watching live or watching it later. And remember to ask your questions on our discussion board. And we'll perhaps see you soon. Clear skies. Bye-bye.
Bye-bye.